Hi everyone, my name is Andreea Vescan and today I'm going to present our collaborative approach of a reliability prediction model based on internal structure and post-release defects using neural networks. First, I will emphasize the importance of quality of software system, discussing the Fenton axiom: a good internal structure of a software system assures its good external quality, metrics used to assess the internal properties, and defect prediction approaches. Then I will present an overview of our approach, providing goal question metric approach to quantify reliability, describing further the design of experiments. The results are presented and discussed next, and a comparison of the neural network model with the regression model is further discussed. Conclusion and future work are emphasized. The motivation of this work is to help in the DevOps practices regarding the measurement of reliability quality attributes and provide the prediction model for defect classes. The quality of software system became more and more a necessity due to their increase in size and complexity. The software systems are inflexible, monolithical, and difficult to maintain. All these hampered the maintenance and evolution of the systems. Therefore, early detection and prediction of software defects plays a very important role in the software industry in terms of quality measurement. It is well known that a good internal design structure has a strong positive impact on external quality attributes. The aim is to obtain a flexible and easily adaptable software such that when extending the functionality of the system, a limited alteration to existing modules should be done. To achieve these easy adaptable systems, we need to assess the internal properties, design principles, design patterns, and design architecture. As a result in this direction, software metrics are very useful as a means to quantify those aspects that are important for the assessment. Thus, we measure the internal properties of the software system by using software metrics. Having into account the reliability definition and the reasoning regarding the vital influence of the system internal structure on its external behavior, the pillars of this research investigation are a metric for reliability definition using the expert related to bugs, and the use of metrics that quantify the internal structure of the system to predict the system reliability. The studies on how to quantify reliability highlight two aspects: reliability assessment, respectively reliability prediction. Reliability assessment relies on collecting data during testing, operation, and maintenance in order to conclude about the overall reliability of the system. Our proposed model to quantify reliability is driven by a goal question metric approach applied for both aspects mentioned above regarding on how to quantify reliability. First of all, the measurement objectives are linked to the reliability assessment, defining a new metric to quantify reliability. Then, we connect the measurement objective to reliability prediction by using the metric defined at the previous step and the characteristics of the software system internal structure. We claim that the four sub-characteristics of reliability are related in a great extent to the post-release faults or bugs found in the analyzed system. We establish weights for each of the four bug characteristics, considering an order relation that establishes a priority in solving these faults or bugs. We have high priority bugs, non-trivial bugs, major bugs, critical bugs, and bugs that were not categorized. The reliability of a class is defined as an aggregate measure by means of the equation that linearly combines the number of different types of bugs. The goal of this study is to explore the relationship between object-oriented metrics and reliability by predicting reliability at the class level. For this, we use the value of reliability computed by the provided equation as a target value and the value of CK metrics as independent variables in the prediction model. In order to predict the reliability, a feed-forward neural network with backpropagation learning is used. In each experiment, we train a neural network-based prediction model using 9 out of data from a single dataset. Each experiment used a different dataset for training. Each prediction model was then validated in 2 steps. The first step was to validate it using the cross-validation technique, which means that we use for validation the remaining 1 out of 10 data for the dataset that was used for training. The second step was to validate the model using data from the other 4 projects from the dataset. Thus, the within project validation was first applied. Project A is considered both for training and testing. As a second part of each experiment, the cross-project validation was performed, thus using the other 4 projects from the dataset for validating the model. For example, GDT training used for PDE, EQ, LU, and my projects are used in turn as project B. The current slide presents the results obtained for both within project and cross-project experiments. For within project, the PDE training obtained the minimum value for the RMSE, bold in table among all each training projects, as you can see. For the cross-project experiments, the minimum RMSE values for each validation set for the cross-project experiments is marked with gray background. For all projects except Lucene trained by Mylene, the minimum value obtained is for Mylene. For Lucene training, the minimum RMFC is obtained for Equinox, and Mylene training, the minimum RMC is obtained for PDE project. The current slide presents the result for the cross-project experiments. In the figure 3, we can discern that the RMSE mean for EQ is the highest among all projects. The GDT project had the largest number of similar RMSE values for all its validation projects, whereas PDE and Mylene have the smallest RMC values. In the figure 4, a plot radar figure was used to emphasize the relationship between the project used as training and the project used as validation. Analyzing the results, it can be seen that the obtained RMSE values may differ depending on which project is used as a basis to train the model. Best RMSE is obtained for PDA training and Mylene training, thus with plugin and task characteristics. The worst value is obtained with AQ project, thus using a project with framework characteristics as training. In conclusion, plugin training finds best RMC value for a task-oriented project, and the framework training project finds the worst RMC for a task-oriented project. The experiments conducted in this paper enable us to state the following observations. One aspect for reliability prediction based on code metrics is considered in this investigation: bugs with different flavors, high priority bugs, non-trivial bugs, major bugs, critical bugs. Other aspects for reliability need to be considered for a deeper understanding, aspects such as changings, number of revisions, number of authors, number of fixes. Various prediction models were compared using cross-project validation, and only one model pre-trained project for within-project validation. It would be interesting to investigate various prediction models for the same project using various releases. Thus, we are now ready to answer to our research question. What is the association between the project characteristics and reliability expressed by bugs when using CK-based matrix neural network prediction model? The experiments using within-project and cross-project prediction models identified that the best reliability by bugs prediction is obtained using plug-in-based characteristics training projects for task-based characteristic projects. The current slide contains the comparison between our current neural network model with the multiple regression model. The obtained results in the multiple regression approach show that using Mylene as training provides the best prediction for the Lucene project as validation. In the current approach, using a neural network model, the best training project was PDE with the best RMC values obtained for the Mylene validation project. An important remark regarding both approaches is that for all training-based projects, except for the current approach with Lucene project, the project that obtained the minimum RMC values is Mylene project. Thus, having as a validation a project with task management characteristics, we obtain the best prediction approach no matter what characteristics had the training project. The motivation of this work is to help in the DevOps practices regarding the measurement of reliability quality attribute and provide a prediction model for defect classes. Thus, firstly, we define a metric for reliability assessment based on the software external aspect that influence reliability. In this approach, we consider software bugs. We study one of the indicators of reliability in the form of the bug count, advocating once again that even if reliability is an operational characteristic of the software, thus remaining faults activation is environment context dependent, post-release bugs influence its value. For example, the high priority bugs may be framed or enclosed as every time the software is executed, a remaining fault is activated, thus relating to reliability estimation. Secondly, the paper employs metrics that quantify the internal structure of the system in predicting the system reliability. The novelty of this paper refers, therefore, at proposing a neural network-based prediction model for reliability defined by one aspect, bugs, using CK metrics, reducing the cost of improvements. As future objectives, we would investigate other reliability aspects, various releases of the same project, and we will consider also various weights for various types of bugs. Thank you for your attention. Please contact us for any other questions or collaboration.